Hi everybody, my name is Dr. Peter Bartocci and I am a Marie Curie Fellow at the Istituto de Carboquímicas, SIC, situated in Zaragoza, Spain. I am presenting my contribution named Two Alternative Fuels for the Reduction of Greenhouse Gas Emissions in the Steel Industry, biocarbon and hydrogen. This wants to be a comparison between the environmental impact of two alternative fuels which can substitute coke with two different industrial processes and so reduce the emissions of the steel industry. As we know, the steel industry, according to the Financial Times, is responsible for 7% to 9% of all the direct CO2 emissions which we have in the world. So it's a big player and has big responsibilities in greenhouse gases emissions. What we present is a two-phase solution. So the use of hydrogen and the use of biocarbon. Biocarbon can be a solid fuel for the substitution of coke, leaving the bulk of the technology quite the same. While for hydrogen, we switch from blast furnaces to electric arc furnaces, which should be fed with directly reduced iron. So we should have a first step of direct reduction of iron through hydrogen. And then we should operate an electric arc furnace, which can use, for example, carbon or the same biocarbon as a fuel and a reducing agent. So the methodology is based on LCA, which is performed using CIMA Pro software and EcoInvent 3.5 database. The impact which is analyzed is more or less the carbon footprint, because as we have said, the problem is the greenhouse gas emissions of the steel sector. And the two fuels are compared on a basis on a functional unit, which is the kilogram or the ton of steel produced. So coming to the LCA of biocarbon steel, this is the biocarbon which we produce in our lab through a collaboration of the University of Perugia, the SINTEF, Norway, University of Agder, and Huazhong University of Science and Technology, situated in Wuhan. So all these experiments aimed at producing a fuel which had low porosity. To decrease the porosity of the biocarbon, we first practiced pyrolysis, then we mixed the char with the liquid pyrolysis oils, and we pelletized the mixture, trying to push the pyrolysis oil inside the pores of char and to make them mix and act as a binder in the pellet production. Then the produced pellet was reheated to facilitate the polymerization of the liquid bio-oils inside the charcoal porosity. And so in this way, we believe to have a better fuel which has a higher strength and also reduced porosity. The porosity influences what is the reactivity of the charcoal, which comes to approaching the one of coke. So this was the plant we developed, which we have already presented in the previous edition of this conference, the MIT A+B conference 2020. And we have mainly first pyrolysis, then mixing and pelletization, and then reheating, as we already said. These are the boundaries of the life cycle of metallurgical coke. We see this is a multiple product process, and we took this process entirely from the EcoInvent database, while in the previous case we used the data from experimental pyrolysis plants to model effectively the production of biocarbon. Then we used once again processes taken from the EcoInvent database on steel production, and we just substitute the produced biocarbon with the coal. So we tried to decrease the use of coal almost to zero in steel production, and substitute it with biocarbon. What we obtained as a result is a decrease in the final carbon footprint of this is the comparison of the carbon footprint of biocarbon and coke, and on the contrary of what we can expect, the average biocarbon emissions are higher. This can be evaluated in many ways. We can consider, for example, that these emissions are mainly due to biogenic carbon dioxide, so they are not taking part to the fossil fuel greenhouse gas emissions. And we can consider that some emissions are due to the fact that the pyrolysis plant itself consumes energy and electricity. So the efficiency of the pyrolysis process is not always good. Also, if we take into comparison the production of coke, because producing coke through coal pyrolysis is more efficient because we have higher yields, because coal has less volatiles than biomass. So if we do a pyrolysis process to produce a solid product, it is obvious that the yields of coal will be higher than those of biomass. So this explains why the emissions per kilogram of produced final solid products are higher for biomass. In the final steel production has a higher emission for conventional steel, because as we say, when we come to the combustion of the final product, coke has important emissions of greenhouse gases, while biomass doesn't emit almost carbon dioxide, because we release what the biomass has previously absorbed during its growth. So the actual reduction of the total emission is about 31%, which is interesting. The aim of the study is to compare or have a preliminary idea of the reduction which can be obtained using also hydrogen. For this sake, we consider the study of Bhaskar and others in 2020, which is a study of the University of Stavanger, Faculty of Science and Technology, Institute of Energy and Petroleum Engineering. So in this model, we see that hydrogen is produced with electrolyzer. And it is used for direct reduction of iron pellet, which is heated at the temperature of 800 degrees. This is not overcome this threshold of 800 degrees, because above 900 degrees we could have sintering. And then, as we said, we have electric arc furnace. These are the mass flow of the direct reduction process, which maybe is the most interesting. And we see that it is performed in a furnace in which iron and hydrogen are in counter current. And the metallization rate of iron is 94%. This means that the metal iron which exits the reactor is about 94% of the metal that entered the reactor. The mass flow of exhaust gases is represented by unreacted hydrogen and steam. So finally, the results of this study performed in Norway show that the average EU carbon dioxide emissions per kilogram of per ton of iron produced are around 1,000 kilograms of CO2. So if we compare with our previous study on biocarbon, the final use of hydrogen could reach a reduction in CO2 emission of 50%. We have to take into consideration that in this study, some of the assumptions are different with respect to our calculation on biocarbon production. Because these calculations are mainly made with the electricity consumption and the heat consumption, while the facilities also imply emissions. So we have to think that the facilities needed to produce, compress, and transport hydrogen, and also the furnaces needed for the processes can have significant emissions due to the fact that, let's say, we can substitute coke with biocarbon in an already existing plant, while in this case, we have to make a completely new plant. Coming to the conclusion, biocarbon can be produced from the pyrolysis, pelletization, and reheating of biomass. Steel produced from biocarbon can reduce its carbon footprint of about 30%. In principle, reduction of emissions using H2 for direct reduction of iron can be higher than 50%. So here we see a comparison of what we can consider A technology against B technology, because this will probably come in the future. And greenhouse gas emissions, not all for hydrogen direct reduction of iron, should not consider only energy consumption, but all the emissions due to the new facility which are needed for this innovative project. I thank you for the attention, and I remember that this project was founded or co-founded by the GTCLC NEG project, Marie Curie project from the European Union.